In this last part of the pencast, I'll talk about polymorphic type inference. And this is probably the strongest selling point of all for polymorphically typed functional programming languages. Because what we'll be solving here by coming up with a good algorithm is the following problem. Given type environment E and expression E, is there substitution, sigma, and the type T such that E has type T in sigma of E. And the algorithm that I will describe now is an algorithm for this that will find sigma and T if and only if they exist. So the algorithm is sound in the sense that if the algorithm comes up with a sigma and a T, T is the type of E and sigma is a valid substitution. And conversely, if there is a T and there is a sigma, the algorithm will find it. And the idea behind the algorithm well, there are really two ideas. The first idea behind the algorithm is to try to construct a type derivation tree. It's in more or less the same fashion as I described in the previous part of the pencast, only in a completely systematic fashion in the form of an algorithm. And in finding the substitution, finding the types, we will solve equations over type expressions. And why do we need that? Well, because whenever we're trying to type an application E1, E2, what we want is, of course, that the type of E1, E2 should be some T, and the type of E2 should be T2, and the type of E1 should be T1, and then we expect that T1 is a function type, T2 arrow T for some T, and then the question is, what is T? So if we can find T, we know that that's the type of that T. So it's really about solving equations of this form. And in order to show how we solve equations, we'll need a bit of terminology. The idea is that whenever we have an application, E1, E2, we introduce a new type variable. A, and then our equation is T1 is T2 arrow A, and then we solve this equation for A. In other words, what is the value of A? What is the type associated with A? In other words, we're finding a type substitution for A. So we're faced with the task of given two type expressions, t and t prime. We find a substitution, sigma, such that if we apply sigma to t and we apply sigma to t prime, we get the same type expression. And moreover, we don't just want any substitution, we want the most general such substitution. This is what we want. So, what does it mean to be the most general substitution? Let's settle that first. Let sigma and tau be type substitutions. We say that sigma is more general than tau if there is a type substitution sigma prime such that tau can be obtained by specializing sigma using sigma prime. So we can specialize the types in sigma and then get tau. That's the trick. So to make this clearer, perhaps it's a good idea to have an example. Here we go. Here's one type substitution that says that t map to u arrow u. And here's another type substitution that says that t maps to v times v to v times v. And we can easily find a type substitution such that tau is sigma prime applied to sigma. If we take sigma prime to be, well, it's obvious how to make these equal. We just make these the same. So let's simply map u to v times v. That does the trick. And then we'll say that a type equation of two type expressions can be solved if there is a type substitution sigma such that sigma of s is sigma of t, and we call such sigma a unifier of s and t. We call it a unifier. And a most general unifier for s and t is a unifier such that it's more general than every other unifier. For s and t. Let's consider an example. We have two type expressions. One is u2, so u1 to u2, and the other is t, which is v1 times v2 to v1 times v1. And it's not hard to see that if we take sigma to be the substitution that sends u1 to v1 times v2 and u2 to v1 times v1, then that is the most general unifier. Of S and T. Sometimes there is no unifier. It's fairly easy to see that if we consider this type expression and that type expression has no unifier at all, because there's no way of assigning types to u1 and u2 such that these two type expressions will be identical. This one has no unifier. One thing I'm not going to show you, but I'm just going to claim, is that there is an algorithm, and I'll call it Unify of S and T, that returns the most general unifier, MGU of S and T, if it exists. This algorithm is standard, and there's a version of it that runs in linear time. Anyway, so that's unification, and we need that for solving equations on type expressions. And now, given that, I can present the algorithm for type inference, and it's called the W algorithm. Here it is. The W algorithm is an algorithm that takes a type environment and an expression and returns a substitution and a type such that sigma of E makes E well typed with type T. And it's a recursive algorithm, and I'll present the cases in the recursive algorithm now. So this algorithm takes an E and a small e, and there's a case for each expression. If the expression E is 0, well, that's easy. We return the identity substitution, and the type of 0 is int. That's easy. If it's a successor expression E1, we call recursively, and if by calling the well-typed algorithm on E and E1, if we then get sigma and int, then we return sigma and int. And if it doesn't return sigma and int, if the type of E1 is found to be bool or something else that's not an integer, we fail. So notice that these two cases correspond quite closely to the type rules, and all the cases that we'll show correspond exactly to the type rules, in fact. For Booleans, it's also very easy. If the expression is true, we simply return the identity substitution and the type bool, and the same for false. We return the identity substitution and bool. It's a little more interesting once we get round to variables, application, abstraction, and all of that. If our expression is a pair, E1, E2, then what do? Well, we recursively call the well-typed algorithm, the well-typing algorithm on E1, and suppose we get sigma 1 and the type T1, and we get, when calling on E2, we get sigma 2 and T2, then we return, well, what do we return? Well, we return the composite substitution sigma 2 composed with sigma 1. And the type is T1 times T2, and otherwise we fail. If these do not succeed, we fail. Okay, and now for the other cases. If it's a variable that we're looking at, well, there are two cases here. If the variable that we're looking at is mentioned in the type environment, and the type environment says that X has type or type scheme for all A1 up to for all AK S, then we return the identity substitution and the body of the type scheme S, because then we can instantiate it later on. Otherwise, if X is not mentioned in the type environment, we fail. So this part of the well-typedness algorithm allows us to make instantiations of variables. Remember the type rule for instantiations. We strip off the quantifiers and then we can instantiate the type variables. And this is exactly what we do here also. For abstractions, if our expression is lambda x e1, then we need to create a new type variable. So let A be a new type variable, an unknown, which is the unknown type of the argument. Let's be a new type variable. Then we call the well-typedness algorithm with type environment, but also add information that X has type A, and then we call, with that type environment, we try to type the body, and then if the result of that is the substitution sigma and the type T, then return, what do we return? The substitution is sigma, and what's the type? Well, the return type, well, this is a function, so its return type should be T, because that's the type of the body. And what's the type of the argument? It's what the substitution tells us should be the type of our new type variable A. So that's abstraction. Now applications, that's where unification comes in. If we have an application, we call the well-typing algorithm recursively. Suppose for E1 we get sigma 1, T1, and by calling recursively on E2 we get sigma 2, T2. Then we create a new type variable. And if both calls succeeded, then we try to unify the types that we got. We call the unification algorithm with the types T1 with respect to the substitution sigma 2, because this tells us what the type T1 really is according to the substitution that we found for E2. And then the other argument of substitution is T2 arrow A. And if we can actually find out what A is, then we're happy. Then we return substitution. Well, it's not sigma, but it's sigma applied to the substitutions that we had before. And the type that we get is the type of A according to sigma. So that's sigma of A. And if something went wrong, if the calls did not succeed or the unification failed, we fail. So that's application. There's only one that's case now. And that's the case of a let expression. So suppose our expression E is let f equals E1 in E2. So here we call recursively the well-typing algorithm. We called it on E1. We get a substitution out of that. And we call the well-typing algorithm on E2, and we don't call it with E, we call it with E prime. Remember, we're trying to do what the type rules say we should do. So E prime is the substitution that we had before applied to E. That's the old type environment, except now we close the type of F. So this is intended to look just like the typing rule. We let F have the closure with respect to E, or sigma 1 of E, and the type S1. And then we call the well-typing algorithm on E prime. And we get sigma 2 S2, and then we return sigma 2 sigma 1, and the type of everything is the type of the body, of course, so that should be S2. And the substitution is the substitution that we found by typing E1, and then what further knowledge we got from typing the body, E2, so that's why it's sigma 2 applied to sigma 1. Of course, this only makes sense if nothing failed. If some recursive call failed here, then we fail. So that's the well-typing algorithm for you. And remember, the idea underlying this algorithm is simply to run the type system backwards, try to apply the typing rules in a bottom-up fashion, from conclusion towards premise. And by doing that, we try to reconstruct the type derivation tree, and every now and then we have to solve a type equation. That happens when we have an application. What I will do now is I will give you an example. And now I'd like to give you an example of how to actually use the algorithm for computing and well typing. What I would like to do is to consider the following small expression. Let f equals lambda x dot x in f of naught, and my possibly not very educated guess is that this should have type int. And let's see if that's true and how we can find it. So the first thing we notice is that there are no free variables in this, so if we want to use the well typing algorithm, it's okay to use it for the empty type environment. And for our expression, let f equals lambda x dot x in f of naught. And then when actually applying the algorithm, we notice that, hey, this is a let expression, so there are now three sub-goals that we need to check. There's the recursive call of lambda x dot x, and that gives us a substitution and a type. And then the second goal is to find the type environment that we use in the second recursive call. So the type environment sets f to the closure of the empty type environment when sigma 1 is applied, and we close T1 with respect to this. And finally, there's the other recursive call. We call with type environment E prime that we've just found, we call f of naught. So those are the new sub-goals that we have. Two recursive calls, and the second sub-goal is finding that E prime. So let's see how those calls proceed. In the first call, finding w of lambda xx, well, that's a lambda expression, so from the case for lambda expressions we see that this gives us a substitution sigma 3, and there's a new type variable that we introduce, a fresh one, and the type that we return is sigma 3 of a, arrow t3. So now it's just a question of finding sigma 3, which is not so difficult, because here this amounts to calling, because this is a lambda expression, we call for type environment extended with binding that x is bound to a. Call that with the body of the function, which is x, and here we see that this gives us the identity substitution and the type of x, which is a. That's safe. So this means that this is the identity, and because this is the identity substitution, this type is a, arrow a. So that's the first recursive call for you, and then we can find E prime. E prime is an f mapped to the closure of this type, where we close with respect to all the variables that are not bound here, and there aren't any bound variables here, so this is just for all a, arrow a, And if we think about it, that's reasonable, isn't it? That f, being the identity function, should have this polymorphic type. Finally, there's the third goal, which is the other recursive goal, the one using e prime that we just saw with the expression f of naught. Well, that's an application. So here there are two recursive calls. There's one for e prime and f is a variable, so this we find by identity and a arrow a. Here what we did here was that we looked up f in the type environment because e prime was f bound to for all a arrow a, and we stripped off the quantifiers. That's what we do when we see a variable, and then we return that. Yep. So that handled the call for f, call for naught. It's very simple because that's the identity function, and then it's int. And now, because we've got these two calls and we need to find a unifier for the type expressions, int arrow a and a arrow a. So to unify those, well, that's very easy. Unifying those, oops, that's just a substitution that sets a to int. So now this gives us the substitution sigma 2 and the type S2 that we were looking for, because sigma 2 is then sigma applied to id, composed with id, which is just sigma, and S2 is then sigma 2 applied to a, which is int. So over here in this call, this returns the substitution sigma 2 and the type int, and this is what we return, and in fact, hey, it's int alright. So yes, this expression does have type int. So all is well.